the KSP of AgBr is 5.4 times 10 to the minus 13 at 25 degrees Celsius. Calculate the molar solubility of AgBr in a 0.05 molar AgNO3 solution at 25 degrees Celsius. I start off with my equation. I'm going to write the equation for the thing I'm dissolving. Okay, I'm going to write the equation for the thing I'm dissolving. And then let's go back to read the question. We'll see what we keep on doing from here, yeah? They're asking me to calculate molar solubility. I get given KSP. Okay, so same as the last question, I'm solving for X. Yeah, I'm solving for X. Okay, so then let's fill out our initial concentrations. Our initial concentrations are affected by what we're dissolving it in. Okay, because guys, remember, initial is T is equal to 0 seconds. Okay, I haven't even dropped in my solid yet. Yeah, I haven't even dropped in my solid yet, which means what do I have at the start? I just have the solid in one place and the solution that I'm dissolving it in another place. Okay, I haven't put my solid in yet, which means the initial is affected by the solution. Okay, so let's look at this now. I'm going to write out here and realize Ag is the same thing, which means Ag is my common ion. Ag is my common ion. So I need to figure out how much of my common ion is in there. So they told me I'm dissolving it in 0.050 molar AgNO3. And then I've already figured out that Ag is the common ion. So that's the thing that goes into my ice table. Yeah, just by looking at the ratio, if I have 0.05 molar AgNO3, how much Ag plus do I get from that? It's a 1-to-1 ratio. So that's how much I have initially. So that just goes into my initial box now. Yeah. So guys, the only thing that changes when you're doing common ion effect is the initial box. 0.050. Okay, and then is there any bromine in my silver nitrate solution? No, which means even though I have some Ag, my initial concentration of Br is still 0. If it's not the common ion, it's not in there. And then the rest is the same. Okay, I still shift that way because I still need to make some of this. Okay, so if I'm still shifting that way, or what's my change in Ag plus X? Good. And then now the only thing that differs is when I add it together, this E part becomes 0.050 plus X, and then this one is still X. Okay, so guys, everything else stays the same. The procedure stays the same. The only thing I've changed is the number out the front, so that changes this number, but the general procedure is the same. I add I plus C to get me my E. My steps stay the same. I'm still solving for X, which means I still need my equation. So my equation is still KSP is equal to Ag plus NBr minus, which is still 0.050. So now I've just subbed the numbers in. The KSP they've given me, 5.4 times 10 to the minus 13. The thing that makes your common ion effect different is this is the situation where you're pretty much guaranteed that you'll end up with some kind of quadratic equation. Like that ax squared plus bx plus c. Yeah, you're bound to get that in a common ion effect question. That's the only thing about it. What I mean by quadratic formula is that if you look at this here, if you just expand it like from maths, like you expand the bracket out, you get 0.050x plus x squared. And then you still get this thing on the right, which is 5.4 times 10 to the minus 13. You can make a simplifying assumption when you're doing the common ion effect. What you are allowed to say is that when you have x that's added or subtracted to another number, okay, so I'm not talking about x on its own. I'm talking about x relative to another number. I want to avoid using the quadratic formula. So I'm going to say in this first bracket here, 0.05 plus x, X has been added to 0.05. What I'm going to say, though, is I'm going to say X is way smaller than 0.050. Okay, X is a lot smaller than it. Yeah, X is way smaller than it. So it's like saying, oh, maybe, let's say, for example, you know what? When you solve for X, it might be like, that's theoretical, okay? This is not the solution, yeah? But let's say X is 2.3 times 10 to the minus 6. Times 10 to the minus 6, there's so many zeros in that, which means that when you add it to 0.050 plus x is 0.050 plus 2.3 times 10 to the minus 6, what you're basically doing, this is what 2.3 times 10 to the minus 6 actually is. This is 0.050 plus, I'll expand it out in decimal places for you, 0.0000023. That's what you're doing. Yeah, if x is a really small number, that's what you're doing. 0.050. When I add a really small number to another number, it's not going to do much to it. Because then if you actually do it, it'll be 0.050023. That's what the actual answer will be. In which case, it might as well just be 0.050. So x is way smaller than other number, which means I can basically say, oh, 0.050 plus x by x is just about 0.050 with x. Okay, so I'm neglecting x relative to the other number. So then I get 5.4 times 10 to the minus 13. And then it becomes really simple, okay? This is my new equation. It's not a quadratic anymore. When you look at this equation, think of it just as a math equation. What do I have to do now to solve for x? X is 5.4 times 10 to the minus 13 divided by 0.050. Sometimes when we did the ICE tables before, we never had to talk about this assumption, yeah? For most of you, this is the first time you've heard about this assumption. So we just want to go through why you know that you need to set it up and things like that, okay? Now, the reason why I'm able to say that x is really small relative to 0.05 or relative to whatever number is in your question is because the KSP is really small. Like in this answer, KSP is 5.4 times 10 to the minus 13. In this answer, KSP is 5.4 times 10 to the minus 13. So like that means that the equilibrium expression is going to be a really small number anyway, yeah? So KSP is AG plus BR minus is 5.4 times 10 to the minus 13. So the whole answer is going to end up being 10 to the minus 13, which means all the numbers that you put in it for AG plus and BR minus is probably going to be a really small number anyway. Which is why you can say, oh, if K is really small, then X, you can probably say it's really small as well. So then you can neglect it relative to another number. Yeah, that's the reason why you're able to make this assumption. So guys, the only time you're allowed to say, oh, X is smaller than another number and ignore it relative to the other number is if K itself, 5.4 and then minus 13 in this case, if K itself is also a really small number. If K is not a really small number, we'll talk about what it means to be a small number in a second. If K is not a really small number, you cannot make this assumption. X is really small relative to another number because K is really small.